Alright guys, so now we're going to go over sections 7.3 and 7.4, confidence intervals for the mean when sigma is unknown. So when sigma is unknown, as in the standard deviation of the population is unknown, we will at least know, because we always know the information of our own sample, because it's our sample. And because we know the information of our sample, we can estimate the normal distribution of the entire population by using the sample distribution that we have. So because we have our own sample, we can always find the standard deviation of our sample. So when we do not know the standard deviation of the population, like in section 2, we can use the standard deviation of our sample and use that to our advantage and learn more about the population standard deviation and the population distribution. So we're going to be talking about t distributions, and we have five criteria for a t distribution. As the sample size n gets larger, the t distribution gets closer to the normal distribution. So if you look at the yellow line, that's a t distribution of size 3. So the sample size is size 3. But as you can tell, the larger, so if you look at the red dash, n is now 12, and you can notice that it's getting closer and closer to a standard normal distribution. So the larger the n, the closer to a standard normal distribution that a t distribution gets. It has the general symmetric bell shape as the standard normal distribution, but it reflects the greater variability with wider distribution that is expected with small samples. When you have a small sample, your variability is larger. For example, let's say I have a sample 1, 5, and 8. There's a distance between 1 and 5, those two numbers. There's a distance between 5 and 3. There's a large distance between 1 and 8. But the larger my sample, the closer my numbers are going to be to each other. So let's say 1, 3, 4, 5, 6, 8, 7, 2. There's not that big of a difference between every number. There's no gaps. The gaps get smaller and smaller because the more you sample, the more variety of numbers you're going to have. The mean is t equals 0, like the standard normal distribution, which has a mean of z equals 0. So recall that a standard normal distribution, the average is always 0. So for this as well, it is 0. However, the standard deviation varies with the sample size and could be greater than 1, unlike the standard normal distribution, which is always 1. Recall that the standard normal distribution, when you know a distribution is standard and normal, then the standard deviation is 1 and the mean is 0. But for a t distribution, it is greater than 1. However, the mean is 0. And lastly, critical t, similar to critical z, but in this case we are not going to be using critical z. We are going to be using critical t for t distributions, meaning we are going to be using a new table. Instead of a z table or table E, we are going to be using a t table called table F. Again, you could find that in your ebook under the important formulas file that I have on Canvas. So the formula. So first things first is assumptions for finding confidence intervals for a mean when sigma is unknown. So the standard deviation of the population is unknown. However, we are going to know the standard deviation of our sample. The sample is a random sample, so it's always going to have to be random. And similarly from before, either n is greater than 30 or the population is normally distributed when n is less than 30. So if you do not know it is normal, right, it should be greater than 30, the sample size. However, if it is normally distributed, then it doesn't matter if n is less than 30 or greater than 30. So the formula for using t distribution. It is the exact same formula as in section 2. The only difference here is, so we have x bar, which is the average of my sample, minus critical t. So now we are going to multiply by critical t, not critical z. And then we're going to divide, similarly from before, by the square root of n, our sample size. However, On top, we're going to have the sample standard deviation because we do not know the standard deviation of uh, of my population. So I'm gonna be using my standard deviation of my sample. However, there are something called degrees of freedom, and degrees of freedom are n minus 1. And what are degrees of freedom? The degrees of freedom, or DF, are the number of values that are free to vary after a sample statistic has been computed, and they tell the researcher which specific curve to use when a distribution consists of a family of curves. We're not going to worry too much of the definitions of degrees of freedom. What we are going to worry about is when to use degrees of freedom, and we are going to use degrees of freedom when we look at a table F, which is table T. So right now I would say pull up table T, have it with you on the side, so we can look at it together, and I'm going to show you guys a quick example of what degrees of freedom, when are they used, and how to read table F. So say, for example, find the critical T value for a 95% confidence interval when the sample size is 22. So if the sample size is 22, then my degrees of freedom are n minus 1, so 22 minus 1, or 21. So then we go to table F. We look at table F, we have degrees of freedom on the left side. You scroll all the way down to 21, because that's my degrees of freedom. And then you look to the right, up to 95 confidence interval. When you see the 95% confidence interval, then you know that matches that. So 2195 is 2.080. That is my critical T. That is my critical T value that I will use for my confidence interval. Now keep in mind, it says in some tables you'll see one tail, two tail. And by one tail, two tail, what they mean is you have a one tail problem, right? That's when you have a one tail problem. That's when it's either greater than or less than, because that's just one side of the distribution. You have a two tail problem when it's an in-between problem, right? You have on the right and you have on the left. So it's a two tail problem. While one tail is either the right side you're looking for or the left side you're looking for. Alright, to estimate a population mean, you have to choose between Z and T. And when do we choose between Z and T? It's very straightforward. This is how you decide to use critical Z or critical T, because the formula is the same. But how do you decide on which one to use? Well, very simple question. Is sigma known? Is the standard deviation of the population known? If yes, then you use critical Z. If no, then you use critical T. However, in both cases, you have a certain standard deviation. In critical T, you would have the standard deviation of your sample. If not, you would look for it. How do you look for it? You solve for the standard deviation using the data set that you have. And then on the left, either for critical Z, you are given the population standard deviation. And for both cases, if it's not normal, right? For both cases, n has to be greater than 30, unless given that it is normal, then it doesn't matter if n is less than 30. So let's solve this example. A random sample of high temperatures for 12 recent Thanksgiving days had an average of 42 Fahrenheit. Assume the variable is normally distributed and the standard deviation of the sample temperatures was 8 Fahrenheit. Find the 95% confidence interval of the population mean for the temperatures. Alright, so we have a random sample of high temperatures for 12 recent Thanksgiving days had an average of 42 Fahrenheit. So sample size is less than 30. However, it says assume the variable is normally distributed. So we know it's normally distributed, so the fact that the sample size is less than 30 is fine. So n is 12. The average of my sample is 42 Fahrenheit, so my x bar is 42. And my standard deviation of my sample is 8, so S, not sigma. So now I have x bar, I have S, I have my n. I just need my critical T. And again, 95% confidence interval. If you go back to the slide before this one, I had showed how to find the 95% confidence interval. My sample size is 12. So I subtract 1, I get 11. And then I scroll. At 11, I go to 95% confidence interval, and I find my critical T. And it is 2.201 from table F. And the 95% confidence interval can be found by substituting all these values. So x bar minus critical T, S over square root of n, and so on. 42 minus 22.201, 8 divided by square root of 12, and from here it is just algebra. And I should get 36.9 less than mu less than 42.1. One can be 95% confident that the population mean for the temperatures on Thanksgiving days is between 36.9 and 47.1 Fahrenheit. That is pretty much the confidence interval that I'm creating here, right? Because I am asking how can I be 95% confident that the population mean for the temperature on Thanksgiving days is between these two. So I am that confident that my average will be within 36.9 and 47.1. I'm 95% confident. Another example, the data represents a random sample of the number of home fires started by candles for the past several years. Data are from the National Fire Protection Association. Find the 99% confidence interval for the mean number of homes fires started by the candles each year. So here is the data below. First things first is I am not given the sample size. I am not given the the sample standard deviation. I am not given the sample average. However, I am given the sample itself. And I have 1, 2, 3, 4, 5, 6, 7 data points. So my sample size is 7. My average is by adding these 7 numbers dividing by 7. And then using your calculator, if you recall from chapter 3, how to find the standard deviation by putting it into a list and then computing the standard deviation. So, solution, the average is 7041.4, the standard deviation is 1610.3, and the DF is 6 because my sample size is 7, so n minus 1, so 7 minus 1 is 6. So I am 99% confidence, so I go to my table F, I go to 6, I scroll to 99%, and I would get 3.707. That is my critical T. And all I have to do is plug those numbers in and do some algebra at this point, as you can see on the screen. And you should get 4785.2 less than mu less than 9297.8. One can be 99% confident that the population mean number of home fires started by candles each year is between 4,785.2 and 9,297.6, based on the sample of home fires occurring over a period of 7 years. And that is the context of this problem and what we are solving for. Alright, now I'll have you guys try these two examples. Again, you could always ask your questions on Tuesdays and Thursdays when we have our live question and answering session. Here are the answers to these two problems. Keep in mind on the last problem, the reason why I round is because we are talking about hours per week, and we round to the nearest hundreds, to the nearest whole number, sorry. Alright, and that was it for section 3. Moving on to section 4, confidence intervals and sample size for proportions. And the reason why I'm teaching these together is because they're not too far off, so the concepts are pretty similar, so teaching them on the same day. Or again, you could always pause the video and maybe just do 7.3 and then later do 7.4, but the reason why I'm putting them on the same video is because they're all pretty similar. So the confidence interval for proportions. First things first is requirement check. Simple random sample, fixed number of trials, independent trials, two possible outcomes, success and failure, probability of success remains constant. Again, these are the same properties and requirements for a binomial distribution. We're talking about a simple random sample, right? So it always has to be random. Fixed number of trials, so I know how many trials let's say 5 tosses, 6 tosses. I have a fixed number of trials. Random independent trials, meaning the first trial does not affect the second trial. Two possible outcomes, success and failure, as in, let's say I toss a coin, it's either heads or tails. There's no third option, fourth options. There's only two outcomes. Probability of success remains constant. Now remember, success and failure doesn't mean win and lose. Success and failure here means the success is what I care for. So if I say toss a coin, what's the probability of heads? What I care for is heads. So getting a tails is considered a failure, as in it's not what I want. And the formula for this is p hat minus e, which is the margin of error. P hat is going to be our proportion, less than p, the proportion of the population, less than p hat plus e. Now what is p hat and what is e? Find the best point estimate. P hat. P hat is x over n, okay? And x is what I care for, is the success. N is the number of success divided by n, which is always and has been the sample size. What is e? E is the margin of error. It is critical z times the square root of p hat q hat divided by n. What is p hat? Again, x over n. What is q hat? 1 minus p hat, as in the rest. So the failure divided by n. So if p hat is the success divided by n, q hat would be the failure divided by n, all over n. So add and subtract e to and from p hat to get the limits, similar to what we have been doing throughout this time. So the margin of error for the previous section we just did was critical t square root of sample standard deviation divided by n, square root of n. That was my margin of error there. This is my margin of error here. We have been speaking about margin of error since section 1. And keep in mind that this is a binomial distribution, so NP and NQ must be greater than 5 for us to solve this problem, or for us to create this confidence interval. Notation: lower limit, P upper limit, or lower limit, upper limit, as in P hat plus E is the upper limit, P hat minus E is the lower limit of my confidence interval. Alright, example. A survey conducted by Sallie Mae and Gallup of 1,404 respondents found that 323 students paid for their education by student loans. Find the 90% confidence interval of the true proportion of students who paid for their education by student loans. Now, first things first is we have to worry about what the question exactly is asking. And the question is asking, find an interval of the true proportion of students who paid for their education. Now, if I go back to the problem, it says, what are the numbers I know about? I know that 323 students paid for their education. So the number that I know is how many paid. The number I care for is who paid. So 323 is my X because that is what I care about. Now keep in mind, if the question was who did not pay, right? Who did not pay. So I care for who did not pay. Then it changes the entire problem. My P, so in this case, let's put it this way. In this case, my X over N is 323 divided by N, which is 1404. So 323 divided by 1404 is 0.23. My Q is 1 minus P hat, which is 1 minus 0.23, which is 0.77. Okay? If the question were to ask, find the interval of the true proportion of students who did not pay, even though the question gave me information about who paid, if the question were to ask me, give me a true proportion of who did not pay, then now who I care about is who did not pay. How do I know how many people did not pay? That would be 320. I would have to subtract 1404 by 323, which then would be 1081, and then that would change my x, because my x depends on the question. So depending on who I'm looking for and who I care for, that's my success. So now that I found p hat and q hat, 90% confidence interval, again, that's my critical z. So you guys recall the whole step of alpha is 1 minus 90, so I take the left side, which is 0.10, divide by 2, which is 0.05. Go back to section 7.2. If you still have questions about this, you can always ask me, but the critical z is 1.65. Or you could use the table in the book that simply gives you the numbers of critical z based on the confidence interval, based on the confidence level. So now I use the formula p hat, which is 0.23, minus critical z, 1.65, times the square root of p hat times q hat, all divided by 1404. And the same thing on the left side, but I add. On the left side I subtract, on the right side I add. I should get the same number. So the way I would do this, because it's kind of messy, I would simply do 1.65 times the square root of that inside, 0.23 times 0.77, divide by 1404. I do that by itself, and then I just add it and subtract it from 0.23, and I get my two upper and lower limits of my p, so my true proportion. And I would get 21.1% and 24.9%. So I'm 90% confident that the percentage of students who pay for their college education by student loans is between 21.1 and 24.9%. So here's another example. So a survey of 6,000 adults found that 58% say that they would take a ride in a full self-driving car. Find the 90% confidence interval of the true proportion who said that they would take a ride in a self-driving car. So again, the proportion, or my p hat, or my x, depends on the question, and it says who said they would. So the people who said they would is 58%, said they would. So my p hat is 58%. My n is 6,000, because that's how many adults, right? So my p hat is 0.58, my q is 1 minus 0.58, which is 0.42. My critical z, again from the previous example, is 1.65 because it's 90% confidence. And my n is 6,000. So all I have to do is plug these four numbers in to the formula, and I got myself my answer. So again, p hat minus critical z, square root of p hat, q hat, multiplied, divide by n, all square rooted, and from here, again, this is just algebra. So my final answer would be 57%, between 57% and 59.1%. So you can say with 90% confidence that the true percentage of people who said they would take a ride in a self-driving car is between 57 and 59%. So there's a 57 to 59% chance that somebody would say I would take a ride in a self-driving car. Alright, so here are 3 examples. You could go ahead, try these examples out. Like I said before, you could always ask how were these done. The reason why I don't want to show how these are done is because I want you guys to ask. I want you guys to try. I want you guys to be attempting these problems and not having this video to answer your questions. Maybe work hard. So here are the answers, and I hope you got those answers. And if not, you could always ask. You could always email me or come to my live session, question and answer. Alright, so lastly, there's this formula for minimum sample size needed for interval estimate of a population proportion. So this is very, very similar to 7.2, where we were looking for n. And in this case, n is the smallest sample size needed to make a good estimate or confidence interval for a population proportion, and it would be n equals p hat times q hat critical z divided by e squared. And e is the margin of error, either given, as in within. Remember that within problem we were doing? So it'll say a margin of error, is, and then they'll give you the number, or they'll tell you within 0.2 or 2, then e would be 0.2. And if they do not give you e, then there is a table. This is the table here. E depends on P and Q. So if P and Q were 0.1 and 0.9, then E is 0.09. If P was 0.2 and Q was 0.8, then E is 0.16, and so on. However, if E is always given. Either it states it directly or says within, or you could use this table. So those are the three ways you can find E. Usually, normally, it is given. So here's an example. A researcher wishes to estimate with 95% confidence, so I'm going to use my 95% to find my critical Z, the proportion of people who did not have a landline phone. A previous study shows that 40% of those interviewed did not have a landline phone. The researcher wishes to be accurate within 2%. So within 2%, that is my margin of error, and again 2%, so that is 0.02. You have to divide by 100 of the true proportion. Find the minimum sample size necessary. So again, a previous study shows that 40% of those interviewed did not have a landline. And the researcher wishes to be accurate within, but what does he care for? The proportion of people who did not have a landline. So 40% is my p hat. Remember, if the question said the proportion of people who did have a landline, but his study was about people who did not have a landline, then it would change my p hat. But that's again, in this problem, it won't really matter that much because p hat and q hat are kind of used the same way. But just always keep that concept in your mind. So p is 0.40, q is 0.60, e is 0.02, my critical z is 1.96. So all I have to do is plug this into the formula. P hat times q hat times 1.96 divided by 0.02 squared, which is 2,304.96. Now again, you can't really have a 0.96, so you round up to 2305 because we are talking about people here. So the researcher must interview 2305 people. Again, we can't have 0.96 people. So based on the context, you should round. Okay. And that is it for chapter 7. We're going to be moving on to chapter 8 next, hypothesis testing.